All right, so I want to take a look at an example problem that kind of shows how to enter some of these homework solutions in MATLAB. And this is an example that's based on the circuit that we did in class. So when you go to any of the problems, they'll open up in a different window and you'll see something like this, right? So usually there's an image at the top with the information about the problem. And then down below, you'll see a script. And that script basically is a template for you to enter your solution. So typically what's going on here is I've got a set of variables that I've given you where it says, for instance, imag equals, and then you get these square brackets. Basically, those things that are identified, these variables that are created down here, are variables that are being looked for in the solution. So at the bottom here, I see the assessment questions. So the first one here, it says magnitude of the phasor, I. So and the variable name, I'll always tell you that is I underscore mag. So that relates to, as I read through the problem, right, it says use AC steady state circuit analysis to determine the phasor for the current I of t, right? So down here, it's asking for the magnitude of that phasor. Then it's asking for the angle of that phasor. Then my next set of questions, my next set of assessments will relate to part B. My next set of assessments will relate to part C and then part D. Okay? So let's take a look at how I would approach this problem. All right? So I was given this circuit. I was told that R is 100, L is that value, and this voltage source has this value. All right, and then it's applied at t equal to 0, and I was told that somehow, some way, the current had an initial value of 0.2 amps. Okay, so what I got to do is I'm going to basically go through those parts of the problem. So A says use AC steady state circuit analysis to determine the phasor for the current I. Now, I did this, and I've said that we're always going to use RMS for our phasors, okay? So that means for me to solve this, I'm going to have to go into the phasor domain and use RMS values. So in the phasor domain, my circuit looks like this. I say I have V like that as a vector. I have R, I have L, and the current going through that circuit is the vector I, okay? Now, as we talked about in class, and you should know, basically I would basically be V divided by the total impedance, which would be R plus J omega L. So we need to identify a few things here. I was told what L is. I was told what R is. I was told omega as well, right? Omega, from looking at the cosine I was given, has to be 2 pi 100. And V, that vector, because everything is in RMS, I need to look at the amplitude and divide by square root of 2 to determine the true value. And I say that has an angle of 0 degrees. Okay. All right. So in this case, I know it's an angle of 0 degrees because it's just a pure cosine. So what I'm going to do is if I want to, I can just solve this in MATLAB. Now I can put this straight away into MATLAB. Now to do that, I need to remember how to enter this. So to enter that phasor V, right? The way that you would do that, the way I typically would do that is I would say, something like this. V equals 9 divided by square root of 2 times exponential J 0 like that. And I shouldn't say degrees because exponential wants everything in radians. All the core MATLAB functions are always expecting angles in radians, right? This is equivalent to, as you would have learned in 3142, or sorry, as you learned when you were a sophomore, I guess, whatever, in analytical, right? You would say 9 over square root of 2 e to the j 0. This is me using the exponential form to write this. I could have, if I wanted to, have written this as 9 over square root of 2 cosine of 0 plus j 9 over square root of 2 sine of 0. MATLAB doesn't have any way to accept anything in polar form. All right, so I would have to do it one of those two ways. I typically will do it this way. Okay. All right. Here's how I'm going to go and approach this. I'm going to go into the script, and I know it's looking for imag and I angle. So what I'll do is I'm going to define a few things first. I know that R, I was told, was 100 ohms. L, I was told, is 318.3 millihenries. So L is 318.3 0.3 e to the minus 3, right? That's how you use the exponential notation in MATLAB. If you weren't sure, you could have said times 10 to the minus 3. That would have been fine. Okay. And then I can say omega equals 2 times pi times times 100. Okay? And then v, that vector is 9 divided by the square root of 2. And I don't even really have to do it, but I'll just do exponential times j0. Okay. All right. Now to solve for this, I'll just go to the equation that I wrote over here, right? This equation. And I'll say I equals V divided by R plus J times omega times L. Right? So I just keep it all symbolic to match my expression over there. Now, this will give me a vector, right? I'm going to leave it. I'm going to take the semicolons off. I can always do that. And I don't have to keep these brackets here, right? I typically get rid of them. And what I do is I don't try to do the whole problem at once. I just try to do bits and pieces. So I'm going to get some of the later assessments right, or sorry, wrong. I just want to do the first one for now. All right, IMAG. Now you should know how to do this. You could go back and you could say, well, if I is a vector, right, I could do the square root of the real part squared plus the imaginary part squared. I could do that, right? But I suspect that most of you also know that if I use the function abs in MATLAB, that will take the absolute value or the magnitude of that vector. So I'm going to say IMAG is that. And I'm not going to put a semicolon because I actually want to see what result I get. Now in MATLAB, the other thing I can do is I can also say I want to get the angle of I. Now again, all of MATLAB's core functions are going to give me values in radians. So what I'm going to do is I'm going to say, I do a unit conversion. All right. I look at this. If I know it's in radians, if I have an angle in radians, right? So I just think of it this way. If I have an angle in radians, x radians, if I multiply by pi radians times 180 degrees, right? That's a unit conversion that I do. Like that, radians cancel, and I'm left with something in degrees. Now, there's other ways, there's functions that will do the conversion for you, but I'm going to do it this way. So I multiply that angle by 180 over pi, and that converts the units from radians to degrees. And I'm going to leave that uncommented because we saw in class what the answers to these were, and I want to see if they match those. So I'm going to hit submit. It'll take it a second to run. And what I see is just like I predicted. It says I passed the first 2 tests, and then I failed everything else. And the reason I failed everything else is I didn't put anything in there. That's okay, and I would recommend that you do it that way. Because it's sometimes what you'll find out is if you made some big mistakes somewhere in here, sometimes you'll get everything wrong, even though it's actually correct. So I would go step by step, okay? And I can go down here and see, okay, IMAG is 0.0285, and I angle is negative 63.4342 degrees. You go back and look at your notes, you'll see that that's exactly what we said in class. Okay? All right. So I've got that right. Now I'm going to look at the next assessment, determine B and tau. So those were things that are in part B of the problem. Determine B and tau in the differential equation. So what this is I have B and tau are 2 kind of unknowns, and I have to solve for those. The way I would solve for those is by figuring out the differential equation for this circuit and then just kind of matching these values to what's there. All right, so if I look at the circuit, if this is it, we talked about this in class. If I just do KVL, I'll see that V of t equals R times I of t plus L di by dt, okay? So this is not quite in the right form as this, because if I look at this equation I gave in the problem, I have clearly a coefficient of 1 on the I of t term. That says that I got to multiply both sides of that equation by R. So I have V of t over R equals I of t plus L over R di by dt. Now that's in the same form that I gave in the problem. And by looking at my pattern matching here, I see that B has to be the coefficient on the V of t. So B must be 1 over R, and tau must be L over R. Okay? So what I'll do is I'll go over to the problem to see if I was right. So I'll say B, change that and say it's 1 over R, and I'll say tau is L over R. I'll change that. And now I'm going to submit. Now I should get the next two things correct as well. So now the first 4 assessments should be right. Takes it a second, and they are. Okay. Now I have to do the next set of problems, right? So determine the steady state response ISS after t equal to 0. Now this is weird. I'm asking you for a time response. So whenever I do those, I look down here and it says, what are the next set of assessments? Determine the amplitude of the current after t equal to 0. And then determine the steady state response after t equal to 0. So the variable is called ISS using the vector t. So if I look here, I gave you a time vector, and I am asking you to basically create the steady state current using that time vector. All right, so let's see how we do this. First thing I got to do is say, what is the amplitude? Now we should know, right? So all of my stuff is in RMS. All my phasors are in RMS. So I need to say that the amplitude would be whatever the magnitude of my phasor is times square root of 2. Okay. So that's done. And going down here to I steady state, well, we know that if I had this vector equal to I mag angle phi like that, right? That the actual steady state current that would represent, if I do the conversion, would be the square root of 2 times I mag, right? Where this is RMS here. And then I convert that to the time domain. I say cosine omega t plus whatever phi is, right? So that's what I'm going to write here. Now, what I got to be careful about is the angle that I have is in degrees, okay? Now notice when I ask that question, I don't think I mentioned this before, but I usually ask for that angle to be in degrees between minus 180 and 180. If you're getting something wrong and you have an angle that's, beyond 180 degrees, that may very well be the reason, because I explicitly asked for the angles to be between minus 180 and 180. And that's pretty standard to do. Okay. All right. So here's what I got to do. I got to be careful about this. MATLAB assumes all trig functions are in radians. So I got to be careful. Here's how I'm going to do it. I'm going to say ISS is I amplitude. Okay. I amplitude times cosine of omega times the t vector I gave you. Right? So I gave you that t vector. Now I have to add the angle of the current, but I have to make sure that that angle is in radians. So because it was in degrees, right? If I have an angle in degrees, the way that I do it at least, because I'm old, I say 180 degrees on the bottom, pi radians on the top. It's just a Unix conversion, right? So if x is in degrees, if I multiply by pi over 180, that converts it to radians, right? So I'm going to multiply by pi over 180, like that. And I am going to submit. All right, and I got that correct. Okay, good. So I got the steady state response part done. Now the next question, part D here, it says determine the complete response I of t after t equal to 0. So I see down here, determine the complete response after t equal to 0. So the answer should be in the vector I, and I use the given time vector t. All right, so to do this, I can go back to the differential equation. So I have basically as my differential equation v of t over r equals tau di by dt plus I of t And as we've said, this guy, the solution has two parts. I of t would have a transient response, which is a e to the negative t over tau. And then it has the steady state response, right? I'm just going to write that as ISS of t because we've already determined what that is. Now, to solve for this, right, we know what tau is. We know what the steady state response is. The thing we don't know is what A is. So as we talked about in class, I need to be given an initial condition. And I was told here that the initial condition is that the current in the inductor before t equal to 0 was 0.2 amps. So what I do is I go here and I say I of 0 is 0.2, and then I plug in t equal to 0 in the equation. So that means I get a e to the 0 plus ISS of 0, right? And then I solve, right? So basically e to the 0 is 1, so I end up with a is equal to 0.2 minus ISS of 0, whatever I got there, okay? So here is how I would do that, right? I would end up saying, all right, I would create a new variable, a, and I would say a is 0.2 minus, now ISS of 0, there's a couple of ways I could do that, right? What I'm going to do here is I'm just going to basically take this expression, right? I'm going to copy it and paste it, and I'm going to plug in 0 for the value of t, okay? And that is basically ISS of 0. So I'm going to get what that a value is, and then I'm going to come down here, and I'm going to say a. So I'm going to write the transient in. So the whole total response is this: a to the negative t over tau plus ISS. So I'm going to say a. Now in MATLAB, e is exponential, right? Times negative t over tau. And I'm going to add to that ISS, which we already have. And that should be correct, and I'll pass all my tests. And it passed all the tests. Okay, it was correct. Now down here I have commented out basically these two things where I can plot. Now that I have everything generated, I can uncomment those. I couldn't have uncommented those previously because I and ISS didn't exist, or they had no entries, and there would have been an error. So I uncomment those now that those are done. And it should make a graph for me, which should be exactly like the graph you have in the notes. So that's going to appear down here. All right, now notice I got sort of a goofy output because I haven't been careful. I guess I didn't mention this before, but below the assessments, I can read the code outputs. All right, so if I look here, somebody somewhere in here, okay, I need to put a semicolon where I have these vectors, right? That's why I'm basically it's outputting these entire vectors, ISS and I, which are probably very big vectors. So let me submit this again. All right, down here in the output section, it's got stuff I didn't put the comments after. And then it's got basically the same thing that we saw in class. All right. So the blue is the total current. The orange there is the steady state. I can see that the blue starts up at 0.2. It's exactly what it should do, right? Because the initial value was 0.2. So this is about as hard of a problem as you're going to see, I think, in general. But this is the basic approach. One thing that you'll need to remind yourselves of is things like some of the functions in MATLAB. Okay. Those are the things that you'll probably need to remember. Critical thing is that all of the trig functions, including exponential, which is a trig function, all expect that they will get entries in radians. All right, so be careful about that.